Homework last night, page 268, 1 to 14. Any issues with any of those 14 questions that we saw in 268? Yep. 14. Bart? 8. You got 8, 10, 13, 14? 12. Okay, so we got 8, 10, 12, 13, 14. It says a 1,500 kilogram car is making a turn with a 100-meter radius with a coefficient of static friction is 0.70. What's the maximum speed the car can go without skidding? You remember what we said when we started this unit? The whole idea of centripetal force, centripetal acceleration, they're always caused by something else. It's not a force in itself. It's not like, gravity that keeps the Earth in orbit around the sun. It's not like that. Centripetal force is always some other force that we're just calling the centripetal force. What's the other force in this question that the centripetal force really is? Yep, friction, yeah. So we're allowed to say in this question, F is equal to mv squared over r. We're allowed to say F is equal to mu times the normal force. We're also allowed to say those two are equal to each other. When we know something about both forces, the centripetal force and the one that causes it, what you're usually going to do is set them equal to each other. So in this case, let's try that. Doesn't work for us, we'll try something else. Fc equals Fm. So we're going to say mv squared over r equals mu times the normal force, which we're on a flat horizontal surface. The normal force is that easy force of gravity, right, that balances gravity. Masses end up canceling here, although you don't have to because you're given the value of the mass. We're solving for speed. Take the r out by multiplying, mu times g times r, then let's square root that. The coefficient of friction is 0.70. Gravity is 9.81. Just make it positive here. R is 100 meters. What do we end up getting when we do the math? 1,700. It's going to be around, I'm going to say 26-ish. We're actually going to round that to 2 digits, right, Stephanie? Because of the 0.70. So we're going to make it 26 meters per second after all. So 4 digits, and 2 digits. Final answer should be 2 digits, right? Now, here's a quick follow-up question to that one. You get a 1,500 kilogram car, which is kind of mid-size, right? There's lighter cars, there's heavier cars. What if you had a big heavy car, like a 1973 Chrysler New Yorker that weighs 1,000 kilograms more than that thing? How does that affect the maximum speed of the car going around this turn? Let's say you had a little smart car, which weighs, I don't know, say 700 kilograms, I'm guessing. How does that affect the maximum speed of the car? Yep. It's not almost irrelevant. It is irrelevant. Yeah, you're right. Good. Because mass cancels. It doesn't matter how heavy the car is. Okay, if you're going to skid out on this turn on a smart car, then you're going to skid out on this turn on a 73 New Yorker as well. Right? It doesn't matter because the mass cancels. All right, next question we need to go over was number 10. That's a good question. NASA uses a centrifuge. We talked about a centrifuge before, right? We saw a question where, not where astronauts were spun around in the centrifuge, but remember we talked about blood spinning around in the centrifuge? The blood wants to go to the outside, at least the heavier parts of the blood want to go to the outside. Not because they're pushed to the outside by centrifugal force. It doesn't exist. Like they want to go to the outside because of their inertia, wanting to take them in a straight line. We saw that Cirque du Soleil video yesterday, right? Where the guy jumped. He jumped kind of in midair as he was going around that circle, and we saw that he went in a straight line. Ended up at the outside, but not because he was pushed that way, because of his inertia taking him in a straight line. Well, astronauts get spun around in these centrifuges as well for astronaut training, as do fighter pilots. They experience a lot of G's on takeoff. Fighter pilots experience a lot of G-force when they're turning quick in their plane. Okay? They have to be able to handle a lot more G's than we can handle. Yeah, I don't know about you guys, but we were on a field trip on Tuesday. When you go around the Mindbender, that double loop, okay, when you're going around the loop, and then you kept going in the second loop early on in the ride. About 3/4 of the way through the first loop, my eyes started going black. Do you guys notice this? Your peripheral vision starts disappearing, and then by the end of the second loop, it's black. You're blind. You're conscious, but you can't see. Anybody else notice that, or is it just me? We probably wouldn't make good fighter pilots because we couldn't handle the G-force that was on that roller coaster. We're definitely not going to handle the G-force that's in a fighter plane, or probably on takeoff for an astronaut in some kind of spacecraft, like a space shuttle even. These guys can't handle huge amounts of G-forces when they start, but they get better because of certain training, certain breathing techniques that they're given, and muscle clenching techniques that they're given, and so on and so on. They can test them to see what they can handle by the centrifuge. Spin them around. They experience G-forces against the wall of the centrifuge. As you spin them around even faster, they experience more G-force. Okay, basically what they do is spin them around until they pass out. See how many G-forces they can handle. Some of these guys can experience 7, 8 Gs before they start passing out. We experienced, those of us who started blacking out on the roller coaster, experienced maybe 4 Gs before we were starting to lose it. Okay, so this centrifuge consists of this capsule on an 8.9 meter arm. It's spinning around at 35 RPMs. We want to find the acceleration that the astronauts experience, and then we want to find out how many times greater this acceleration is than gravity. In other words, the G-force, how many Gs it is. We got a radius here of 8.9 meters. What's this 35 RPMs? People get this one mixed up. Which variable is that? Yep, it's frequency, right. I would say probably 2/3 of you would say it's frequency, and probably 1/3 of you would say it's period. RPMs, revolutions per time, is going to be frequency. Now, we don't want it per minute, right? We want it per second, right? So what are we going to do to convert that to revolutions per second? Divided by 60. What do you get there? 0.58, exactly. Okay, 4 digits is good enough there. But we probably want to have more than a couple of decimal places there. So 0.5833 hertz. What else we got? That's it. Boy, this is a lot like your quiz question, isn't it? It's a lot like your quiz question. We're going to say A is equal to V squared over R, but we don't have V. So let's say V is equal to 2 pi R over T, but we don't have T. We're going to say T is equal to 1 over F. 1 over 0.5833 hertz. Let's figure that out now. Here's a little trick, guys. I don't know if you guys ever noticed this in the calculator or not. You can go 1 divided by 0.5833, or you can just say 0.5833 x to the minus 1. That's the same thing as saying 1 over that. 1.714 seconds. Now let's say 2 pi r over 1.714. 2 times pi times, what was r? 8.9 meters times 8.9 divided by that period. 32.618 meters per second. It doesn't seem like that fast. You guys go that fast on the highway all the time. But here's the thing. Imagine, for perspective, this room is about 9 meters wide. Okay, about 9 meters from here to here, from the front to the back. Okay, so about that 8.9 meters, right? You guys go 32 meters per second all the time on the highway. But imagine turning in a circle in your car at that speed in a circle with a radius the width of this room. Okay, that presents a challenge, right? Okay, you can turn at 32 meters per second, but you're always turning in a very, very wide sweeping turn on the highway, right? You're never going around a turn that has a radius of this room. Okay, that would be incredibly fast. You would skid right off the road. Okay, but if you didn't somehow skid right off the road, then you would experience a lot of G's as you're in that car going around that turn. Let's figure out what A is now. 32.6 squared divided by 8.9, 119.5. We're going to round that to 2 digits. Right? This is 2 digits. This is 2 digits. Final answer should be 1.2 times 10 to the 2 meters per second squared. Okay, half done. Now we got to find the g's. How many times greater is this acceleration than the acceleration due to gravity? Pretty easy question, actually. You're going to have to do this on your West Ed assignment. It's the acceleration, the unrounded number, 119.55, divided by 9.81. Simple as that. The number of g's is the acceleration divided by the acceleration due to gravity. So let's divide those two numbers. 12.1 or 12 g's. Good luck staying conscious for that one. Okay, 12 g's. That means if you weigh 150 pounds, okay, that's about what I weigh, 150 pounds, then you would feel like you weighed 1,800 pounds. Okay, that's hard on the body. Okay, 1,800 pounds of weight on your body is hard on your body. And you're not likely going to stay conscious through that. If you sustain that acceleration, then you might not even stay alive through that, let alone conscious. That would be a high number, an incredibly high number, even for pilots, for fighter pilots or for astronauts. Normally couldn't sustain that either. Okay, got it? Make sense? Remember this? Remember what's in red here? Okay, blue is your quiz, basically, right? Red, you're gonna have to do that a few times on your assignment, so remember that. Next question was number 12. 12 says, determine the acceleration acting on a person standing at the equator. Interesting question. You're standing at the equator. The Earth is spinning, right? You experience a centripetal acceleration. Let's say A is equal to V squared over R. We don't know what V is, though, so let's find it. It's 2 pi R over T. Wait a second. Wait a second. What's T? We have to attack this some other way. Okay? It's a day. How long does it take the Earth to go around in a circle on its axis once? 24 hours, right? So you, standing at the equator, will end up back where you started all the way around the circle once after 24 hours. I think it's 24 hours is 86,600 seconds. Is that right? Let me check that. We multiplied 24 by 3,600, right? So 2 times pi times, big number here, 6.38 times 10 to the 6, divided by 86,600. Figure that out. Is that right? Or did I make a mistake there? Is it 86,400? Okay. I was thinking it was 600, but then somebody told me I was right there. So what does that work out to be if I go 400? A little bit bigger than 462? You see what I just did there? I didn't feel like entering everything again. So I divided by the wrong number. What did I do? I multiplied by the wrong number again to get back to the top. And then I divided by the right number, 86,400. So it just saved me time there, right? 463. So it makes it a little bit higher. Would you have imagined, as you stand on the Earth at the equator, that you're actually traveling at 464 meters per second, almost 1.5 times the speed of sound. We're breaking the sound barrier right now. We're going faster than the speed of sound right now as you sit here in your desk. So why don't you hear some kind of sonic boom, or why don't you feel it? Why don't we feel it? Why don't we feel that speed? Like, man, if you're going 100 kilometers per hour on the highway, you stick your hand out the window, you feel it, right? Why don't we feel this? Yeah. Well, no, because the radius is very large. You're right about that. Okay, but bottom line is we're still moving 400 meters per second, 464 meters per second. Why don't we feel it? No, we're used to it, yeah. Not quite, though. That's not quite why we don't feel it. Yeah. Kind of. You're on the right track here. Yeah. Gravity, kind of. Gravity is what keeps us from flinging off into space, right? Like, we want to fling off into space in a straight line at 463, but gravity pulls us in and keeps us from doing that. Yeah. Yeah, that's right. But if you go take a vacation at the equator, you're not going to feel it either. You're going to feel the same things you feel right now. Interesting. Yeah. Well, kind of. We are moving, but we're moving with the Earth, right? Stephanie, when's the last time you flew in an airplane? Over the summer? Where'd you go? Las Vegas. Oh, nice 3-hour trip to Las Vegas. It takes you 24 hours to drive. Literally 24 hours and 1 day to drive to Las Vegas. 3 hours and 2 minutes, I think it is, to fly to Las Vegas. The airplane's going pretty fast then, right? Like somewhere about 900 kilometers per hour up in the air. Do you feel that? No, how come? Because you're moving with the airplane, right? You're moving at 900 kilometers per hour, but the airplane's moving with you. You don't feel it. Here we're moving even faster, way faster. But why don't we feel it? Because the Earth and the atmosphere, somebody said the atmosphere part, the Earth and the atmosphere are moving with us. So that's why we don't feel it. That makes sense? All right. That's the speed. What's the acceleration now? Let's say 463.97 squared divided by r, which is 6.38 times 10 to the 6. .03. What's gravity? 9.81. So gravity has more than enough strength to hold us in, right? More than enough to counter the 0.0337. Okay, that's what we need. That's the centripetal acceleration that we need to keep us on the surface of the Earth. We have 9.81 to keep us on the surface of the Earth. So we got no danger of flying off into space because we exceed the acceleration that we would need to keep us on the Earth by a ton. Yep. Well, we're speaking specifically of the ground here. Okay, well, so I'm sorry, can you clarify your question then? Yeah. Okay. No. Well, yes, you are. Yeah. No, you're not bigger than gravity. You're never bigger than gravity, right? Um, Stephanie's question, and correct me if I misunderstand the question, but I'll rephrase it, and hopefully I've got the right interpretation of it. Stephanie's question, good question. If you're flying, you're not on the Earth anymore, right? You're in the atmosphere, but you're not on the surface of the Earth. Well, the atmosphere and the Earth can be considered in some cases to be one system. But here's what happens when you're flying. Like, okay, let's say you were just maintaining the same position above the Earth, which you're not, of course. You're going 900 kilometers per hour relative to the Earth, right? But for simplicity's sake, let's say you're going the same speed as the Earth. But here's the thing. Your radius is higher. Okay? So the centripetal acceleration required to keep you from flying off into space would be lower because R would be higher. So it would be a little bit less than 0.0337 that you'd need to keep you from flying off into space. But the flip side of that is, well, when you're up higher, gravity is a little bit less as well. The further you are away from the center of the Earth, the lower gravity is. But basically, the two counter each other to the point where, you're still fine. There's still no danger of flying off into space. You want to fly off into space, okay, you got to overcome 9.81, not overcome that. Okay. All right. 13. An ant climbs onto the side of a bicycle tire, 0.4 meters from the hub. There's my ant, 0.01 grams. Can hold on with this force. That's pretty good, actually, for an ant that's that light, to hold on with that force. What frequency did the tire fling the ant off, assuming the wheel is spun in a horizontal plane? Think about what this question is. Okay, we're looking for the frequency that the ant would fling off at. You could make this into another question, almost like question number 12, where we could find out what frequency would the Earth have to be spinning at to fling you off, right? But the acceleration that you would fling off at would be like 9.82 meters per second squared, right? You'd have to overcome 9.82 meters per second squared. So almost the same question, except obviously we're dealing with different numbers here. Okay, we've got a radius here of 0.40 meters. We've got a mass of 0.010 grams, which, you know what? I don't like moving the decimal place over here. I'm just going to say 0.010 times 10 to the negative 3 kilograms. It's not scientific notation, but that doesn't matter. It's easier just to tack on a 10 to the minus 3. That way we don't have to worry about counting the wrong number of decimal places or whatever. Here's the force that this guy can hang on with. Any ideas? We've talked about this a lot of times, right? Not sure what to do with this? Think of something that's valid to start with. I don't care if it's going to get you the answer. I don't care if it's even going to lead you down a wrong path. I'm fine with that. Think of something that's valid that I can start with. Give me one thing. Carrie? The period? Can you give me an equation or something? Okay, so period is equal to 1 over frequency. So therefore, frequency would be 1 over the period, right? All right, good. But that doesn't seem to help me. All right, that's fine. That's fine. It's a valid equation, right? So you've written down something that's perfectly valid. Good. Give me something else, Jacob. F is equal to m times a. Good. Okay, force is equal to m times a. Good. I'm going to actually change that a little bit because we're dealing with a circle. And I'm going to make a v squared over r. Because specifically, okay, the force is mv squared over r. Is that going to help me? I don't know. It's not going to give me frequency, but it might give me something at least, right? Okay, let's try solving for, I think we can get v there. F times r, divide that by m. Let's square root that to get v. So it's 4.34 times 10 to the minus 4 times 0.40 divided by 0.010 times 10 to the minus 3. And we got to square root all that. So let's go with inside the bracket, or inside the square root sign first. 4.34, 10 to the negative 4. Now let's square root that. So the speed, the maximum speed that this ant can go, 4.167. Okay, we just found something. All right, but it's not what I'm looking for. Did I waste my time? Listen, it's never a waste of time. If you solve for something valid, even if it doesn't help you, it's never a waste of time. Something else, Stephanie? Okay, v equals 2 pi r over t. That's a valid equation. It's going to help me. I got v, I got r, solve for t. Stephanie, do you have the value of t there by any chance? No? We're going to say 2 times pi times 0.4 divided by that 0.6032. Well, now it's easy, right? 1 over 0.6032 seconds. Notice what I'm going to do here, x to the minus 1, 1.66, 1.7 cycles per second, or hertz. You solved this problem, right? I didn't solve this problem. That's a tricky question. Okay, that was a tricky question. And you solved it. I didn't help you at all, except by saying, what's valid? The only question I asked, right? What's valid here? And you guys told me 3 things that were valid, and guess what? Surprise, surprise. It ended up giving us an answer. Okay, that's how you should tackle questions like this that are challenging. Just think of something that's valid. Who gave me f is equal to 1 over t? Who gave me that one first? Carrie did? Ended up being the last thing I used. I don't care that she gave it to me first. I don't care even if I didn't even use it. She gave me something that's valid. That's what you should do. Think of things that are valid and go from there. Sooner or later, it'll work out for you. Okay, let's see if we have time for 14. Time's a little bit short here, but we probably won't actually. But see what we can do here. 2 pulleys are connected. Oh, we need a picture, don't we? Yeah, there's the picture. All right, you know what, guys? Remind me on Monday. We'll take a look at question number 14 if you didn't get it already. Okay. Let's have ourselves. You know what I was going to say? Let's have another quiz on Monday. We won't do another quiz on Monday, except for those of you who want to rewrite the quiz that you just did. Okay. For that, pop in during scheduled help at lunchtime, either Monday or Tuesday, and you can redo that quiz we did today. All right. Have a good weekend, everyone.